Lab-on-a-chip is a device that integrates several laboratory functions on a single chip of only millimeters to a few square centimeters to achieve automation and high throughput screening. Some of the benefit is that it consumes less fluid reactant volume because it only requires a drop of the reactant, and it's faster to analyze due to short diffusion distances. It has fast heating, high surface to volume ratios, small heat capacities. Because of all of these reasons, it's much more compact, allowing for global accessibility. One of the examples is that there is a lab-on-a-chip research that involves ways to diagnose and manage HIV infections in third world countries. So for example, instead of going to take the blood sample all the way to a lab to test for an HIV positive or negative, you could drop the blood on a single chip which will provide all the information. Unfortunately, there are some disadvantages. Because this is a very novel technology, it is not yet fully developed. Because of increases in microscopic and physical and chemical effects such as capillary forces, chemical interactions, and surface roughness, small-scale reactions can sometimes be much more complex for a lab-on-a-chip than our conventional lab, so it is actually harder for us to put certain reactions in much smaller scales. Some of the problems arise because this is a lubrication flow. Because it has a very small height to length ratio, it can only have laminar flow. Laminar flow means that it has no turbulence, which leads to no mixing of the materials. This may lead to some reactions not occurring on lab-on-a-chip because there is no mixing. This is a huge problem for lab-on-a-chip if it can't perform its purpose. One of the ways to overcome this challenge is by inserting a herringbone mixer into the channel, which is basically a microscopic fin that gets inserted into the pipes to cause artificial turbulence to make reactions happen. Another problem that is caused by this lubrication flow is the pressure problem. Because the viscous force dominates, more fluid is stuck to the wall, so not much room for flow is there for the fluid to go through. This tendency causes a force that tries to expand the fluid, which requires them to have high squeezing or normal force. In a closed cavity, thin film flow, we calculate the force exerted by the fluid on the wall. When you compare the normal force to the tangential force by looking at their ratios, it turns out that the normal force is much larger than the tangential force. This means that it takes an enormous force to drive fluid out of the thin gap, leading to most of the fluid sticking to the wall. And in order to drive the fluid flow, you need a really big pressure gradient along the length for the fluid not to be stuck on the wall and flow through. However, this is very difficult because it's such a microscopic environment.